Welcome, everyone, to one of my absolute favorite lectures. This is on the topic of lighting controls. So, we're going to dig into some of the devices, including control surfaces and sensors that we utilize to manage our lighting systems and really get the performance out of them that they are capable of. And then we'll take a look at how we can use those devices to create some fairly standardized control schemes, which are well established and well utilized throughout the lighting industry. So the first question is, why controls? Why do we bother with controls? And some of you should recognize this graph all the way back from the first week of lighting, which was in the Layers of Light lecture. This is showing the incredible progress we've made over the last, well, this is a decade, but over the last 20 years, the incredible progress in efficiency that lighting systems have made in buildings. And a big part of that is obviously LEDs. In fact, LED efficacy is the primary driver of this trend towards increasing energy efficiency in architectural lighting systems. However, LEDs are inherently controllable. What I mean by that is every LED has a microcontroller on board because their driver is essentially a microcontroller. It's what you need to make an LED an LED. And so that makes all of these devices inherently controllable if we make the effort to do so. And realistically, the incredible effectiveness of LEDs isn't truly realized without advanced controls. And so that's the next step down this process of really realizing the next generation of energy codes is our control system, because no matter how efficacious an LED is, it's not using any energy when it's turned off. Now, let's take this a step forward, though. And these are two words that I'm going to be utilizing throughout the entirety of this lecture, and that is intuitive and convenient. And the reason these are going to come up over and over again is because a control system is worthless if your users don't actually interact with it. So architectural controls must be intuitive and convenient, because confusion is the cardinal sin of controls. Confused or inconvenienced users simply won't interact with the system. And taken the opposite direction, the pinnacle of pragmatic design, the pinnacle of architectural lighting design is a effortless system that just provides the right light at the right time for the right reasons. And that's what controls can do. Not necessarily all the time, though. And so really, in a lot of ways, the goal is for your occupants to never notice the lighting system at all. And if they don't notice it, even when you're changing the light throughout the day, that means you've really done your job right. So here's a couple examples of what I'm talking about here. So this is, well, let's actually start with this old school disaster right here. This is maybe intuitive, but it's not convenient, because every single device has a different switch, and to get the right look in your space and the right amount of light in your space, you're going to have to flip a bunch of switches and play with the dimmers. And so it's a lot of effort to get to where you want to be. So this is intuitive, but certainly not convenient, and definitely an eyesore. Now, you can go too far the other direction, though. And you can have a control surface like this, which is elegant and beautiful. However, it's not intuitive. What is this control system doing? Is it even controlling lights? Because honestly, looking at this surface, I don't really know. So let's take this forward and consider controls that meet the criteria of being both intuitive and convenient for the occupants of your spaces. So let's dig into control surfaces. And first up, of course, is the conventional switch. And there's a lot of ways that we can realize switching. So a switch is a very simple device. Essentially, it just provides a break in your electrical control system and shuts off the power to the downstream devices. So this works, of course, for everything, not just lighting, but any powered loads you have in your space. Switches are great because they're intuitive and they are dirt cheap. In fact, it's so simple, a parrot can use it. I joke about that because I actually installed a switch on my parrot's cage so that she can turn the lights off over her cage. So idiot proofing is a great thing, and switches are essentially compatible with everything because you're just cutting the power when you're using a switch. Now, there's a couple different ways we can approach this though. And the basic switch is a wall box switch like the one I'm holding. And this is something you're wiring directly into your building power, right? So this is going to be on class 1 wiring at 120 volts or sometimes 277 volts. And these can be a challenge to retrofit sometimes, especially if you don't have the lines run down to where you want to locate a switch. So what is our alternative? Well, one good alternative to switches are actually wireless switches. So it doesn't require a lot of power to use a device like this. So we can simply set this up in a retrofit situation. This can mount on the wall. I don't even have to put a hole in the wall. And so I can get that switching control as long as I have a receptive light source on the other end of that wireless protocol. I can get switching controls, add it to the wall wherever I need it to be, and not run any additional wire and not punch any additional holes in my walls. So that's a great option for retrofitting. Onto dimmers. So dimmers are basically the thing that you truly need to get the incredible range of complexity and nuance out of any light source. And I know this seems like a simple control, but I can't say enough about just basic dimming. And you'll see that tomorrow in practicum when we're using a DMX control system. Essentially, all you have, despite the dazzling array of complexity you can get from that system, all you have is a whole rack of dimmers. It's each color channel for each type of light source, and you can dim it between 0 and 255, and you can set the timing. That's basically it. So dimming is the key to unlocking the complexity of light. Now, simple wall dimmers like what I'm showing here, they're intuitive, they're cheap. However, compatibility matters. And we're going to dig into that in a little more detail in just a few minutes. But remember that you can't just attach any light source to any dimmer. You do actually have to verify the compatibility of the dimming protocol. So similarly to switches, we're going to have wall box dimmers. Again, that's going to be the class 1 wiring at 120 or 277 volts. And the basic function is it's reducing the power supply to the downstream load by reducing the total amount of power flowing through that line downstream of the dimmer. Of course, this means the dimmer has to eat the difference in that load, which means that a lot of that energy is being dissipated right at the dimmer. Again, wall boxes can be expensive to retrofit in certain situations. So we can always opt for a wireless option. And this is actually a switch and a dimmer. So that's a great way to go. But there's also low voltage dimming protocols. So things you can do with class 2 wiring that doesn't require an electrician to install. They can still have pretty long runs to get from wherever you want to locate your dimmer to where the light source is actually located. However, it's significantly less difficult than a full class 1 system if you don't have wiring nearby to utilize. And of course, we have scene selectors. Scene selectors are a great option. Now, they are convenient, star, intuitive, star. And the reason I starred those things on the slides is because scene selectors can be and should be convenient and intuitive, but are not necessarily, as we saw on one of the opening slides for this lecture. So it is important to make sure that these scene selectors are set up in an intuitive and reasonable way, and that it's clearly labeled so that it's doing what you expect it's doing when you press the button. So you shouldn't ever press the ceiling off button up there and have the lights in the next room turn off. You'd be surprised how often that can happen when these things are poorly commissioned. And so commissioning matters when you're using scene controllers. Again, you want to ensure compatibility. So compatibility is even more important here with scene selectors. Typically, these aren't running on wall voltage, line voltage, though I will say line voltage versions do exist for scene selectors, but they're not that common. Really what you're looking at here is a digital control protocol more often than anything else. And you are using the scene selector to send a control signal to a range of luminaires in your space. And those luminaires need to be able to respond to that signal. So compatibility is not just important to check, it's required. If you don't have compatible fixtures, you don't have a scene controller. Typically, these things are all running on embedded microcontrollers, and oftentimes they have a configuration layer that is concealed from your typical end user. So you can usually go far deeper with these things, either with a companion app or a concealed control layer, like on this graphic IQ that I'm showing here to my right. Now, of course, these are much more expensive than just a basic dimmer or switch. However, almost always you can justify it if you're using it in a place that really needs one. You can justify it in terms of the increased versatility of a space, say a lecture hall, a multi-purpose room, right? There's a variety of scenes you might want to use for different types of activities in your space. Even your dining hall in your design projects definitely is intended to be both a dining hall and a place just to spend time. So it might be worth considering multiple scenes if you have extra design resources available to your team before the end of the semester. That's not a requirement, but it is something that a space like that likely would want to utilize. On top of this, of course, this comes with increased savings, increased energy savings, because you can quickly get to the light you want and not leave on lights that you're not utilizing for that particular use case. So you're just going to see a lot more versatility from your luminaires, both in terms of the human-centric portion, but also in terms of the energy savings. And then finally, the last option we have on the topic of control surfaces are graphical control surfaces. Again, these can be extremely intuitive. In fact, they can be the most intuitive of all of these control options. And that's because they can have a responsive interface that reacts to the way you're utilizing it and adapts in real time. So GUIs are a great way to control lights. That said, they typically aren't nearly as convenient because they're typically quite a bit more complex. Of course, they are also going to be backed up by some sort of microcontroller, almost always utilizing a digital control signal. Again, you're going to have that concealed configuration layer, maybe in the form of a companion app, but also in the case of this device right here, which is actually a wall-mounted graphical control surface, you can see the setup button, and you would just password protect that in an architectural setting so that you're locking out your average user and restricting that to the building management. The big advantage of these types of systems is they are going to allow you to set up two-way communication. Sometimes scene selectors can do that, but not usually. Usually you're going to want a system more like this, a centralized control system to enable two-way communication. Why do we care? Sensors. Sensors can make your lighting system dramatically more intelligent and more responsive to the needs of your users. So we'll get into those in just a moment. But that's the main thing you would utilize a system like this for, is having that kind of interactivity, two-way communication. Even your luminaires can report their current status. So you could quickly identify a luminaire that's gone down or is disabled or unpowered in a different part of the building that you can't immediately see. So it's great for management and it's great for maintenance because the luminaires can self-report their maintenance needs even. End user touch screens oftentimes aren't that appropriate for a variety of architectural settings, because first off, you have a configurable display. So, there's a big question there of whether or not you want that much capability in the hands of your occupants. Depends on the type of space, depends on who you expect in the space, right? If it's a public facing space, this is probably inappropriate. If it's a private space, then you're more likely okay. You definitely need to be able to lock these down. And also you have durability issues with touchscreens over the long term. And naturally, the last concern is the cost associated with this. So you definitely need this to be in a space that really justifies the use of a more advanced control system. Let's talk briefly about where we want to place our controls, because where you place it matters. Because remember, we have to meet that aesthetic of intuitive and convenient. So let's break this down. What are the aspects that we're considering when we're talking about convenient location of controls? Imagine you walk into a dark space. The first thing you need is a switch or a dimmer by the entrance, of course. But moving beyond that, the question is one of point of use. So a great example in a classroom is, of course, behind the podium, because this is an important point of use where you might activate the projectors from and therefore need to be able to turn off lighting near those projector screens. So point of use is important. And the final aspect that I want to mention is line of sight. And what I mean by that is that your controls need to be within a line of sight to the devices they're actually controlling. Because it makes no sense to be around the corner from your light sources. I've actually had one wedding venue set up this way once over in Bellefonte. That was a fascinating experience. To get the dance floor lighting right, I had to have my wife run around the corner and flip switches and shout at me which switches she was flipping, so I could shout back what was happening with the lighting in the main space, because you couldn't see 75% of that space from where the switches were located. So you do need a line of sight to the fixtures. Now let's add on to this and talk about making a control system intuitive. So for example, let's take a really simple approach here and say we have 9 luminaires throughout this space. Let's split those up into zones. So we've got zone 1, zone 2, and zone 3 over on the far side in the orange. Now, when you come to the switches on the wall, it's really important to also ensure that the orientation of the switch relates to the orientation of those zones. So if you have this on, say, this north wall right here, and you have from west to east, the green zone, yellow zone, orange zone, then those switches also need to correspond to those zones in the same order. So logically ordering your controls is an important part of making that system intuitive. Clear labeling, also important part of making things intuitive. And redundancy. I know that redundancy seems like it might be wasteful, but when it comes to lighting controls, redundancy is actually pretty important. And as you can see, what I'm suggesting in this space is the exact same set of zone switches placed by both entrances and by the podium. And that's simply so that you can get the same results from different locations, regardless of how you enter that space. On from control surfaces, let's talk briefly about dimming. And I don't want to get too deep into this because this rabbit hole goes way down, but I do want to introduce you to some basic concepts here. So let's say that we have a dimmer like this one right here. And what we're going to do is linearly dim a source according to the settings on the dimmer. So if I bring the dimmer down halfway, the light source will be at 50% of the lumen output it was at 100%. So what does that get us perceptually? That's weird. So here's a graph of the perceived light for that linear dimming approach. And what we see here is that almost all of the change is happening at the very bottom of that dimmer. In fact, between 0 and 25%. And if any of you remember like the super old school iTunes, like the original versions of iTunes, and you would have the volume control on that, and all of the change would be happening right at the bottom. Like it'd be way too loud, way too loud, way too loud, and then off. Well, that's exactly what's happening here. So let's give a more specific name to this, and that is that perception. And this goes actually for almost all of our senses, but also definitely for the perception of brightness. The perception of brightness is logarithmic, meaning that the amount of change we perceive when you're down at these low dimming levels is much greater than the amount of change we perceive when we're at the higher output levels. So that's what this looks like. The human perception of the change in brightness is going to fall off as the stimulation baseline increases. Okay, so let's take a look at this a different way. How about a logarithmic curve? So here we have a logarithmic dimming curve, which means that now this controller here is going to change the lumen output of the source the least when we're down here. And when we're up here, the same amount of movement in that dimmer will change the lumen output of our light source much more. And the goal here is, of course, a linear perception of the increase of brightness. And so it's rarely going to be this neatly linear. This is a kind of an idealized case. However, the important point here is that logarithmic dimming is perceived as more steady, more linear than linear dimming is. And that's because our perception is basically logarithmic. This is going to come up tomorrow when we start utilizing the DMX control systems, because the DMX control system is just a linear control system. Now, you can add logarithmic curves to it, but we're not going to go there. So what you're going to be doing is using linear dimming controls like this. And what that means is your lowest settings will create the most perception of change, and your highest settings will create the least. That's just a consequence of our perceptions. Taking a look at some common analog dimming methods. So these are these kind of common analog dimmers like the one I'm holding here, right? So the most basic thing, and all of these, right, are going to be in line with your electrical system. So it's going to be stepping in the middle and changing the power supply to your light source. The most basic approach is simple resistive dimming. Now, this is old school, and that's why I'm showing a device like this one, because it is an old school device. Basically, with resistance dimming, you just have a variable resistor, and every bit of power that is not sent along to your light source, the dimmer eats right there at the dimmer. These things get real hot. In fact, you can actually create set fires with them, and that's a real thing that has happened in the past, and is a big part of the reason why we've largely moved away from simple resistance dimming, even though it gives us this very straightforward approach to dimming where we decrease the power and it's going to increase the dimming by supplying less power to the light source. I'll give you a hint. LEDs don't much care for that, but it's not nearly as hard on LEDs as forward phase dimming. And with forward phase dimming, what we're doing, instead of just eating all that power at the source, we're actually going to feed a lot of that power back along the neutral. So these are quite a bit more efficient than a simple resistance dimmer. And also they don't get fiery hot when you're dimming them to low light levels. Basically, the way these things work is by cutting off the front part of that sine wave. So as the AC power sine wave is coming through the dimmer, it'll chop off the leading edge in order to supply less overall power to your downstream light source. And of course, we have the more modern version of this, which is reverse phase dimming. And so reverse phase dimming is exactly what you think it is. It's going to take the back part of that sine wave and chop it off. And that way you can get increased dimming, again, by decreasing the amount of power by shifting that cut further along the sine wave. So these are our basic analog dimming methods. Now, here is some of the challenges with this, because remember I said earlier that we're basically not specifying anything but LEDs anymore. So the real question is, how do LEDs interact with all of these types of dimming? And it can be a real challenge. And there's a couple aspects of this challenge. First off, we have inrush current. So LEDs aren't actually just constantly on. In fact, the pulse width modulation is using a square wave. And so LEDs are constantly flickering on and off, just at a very high rate above what we can perceive as flicker. So LEDs are constantly cycling on and off. That's called their duty cycle, which means that when you combine that on off with a forward phase cut, what you get here is an inrush spike on every single duty cycle. And so that inrush spike can really be problematic. And this is specifically forward phase dimmers that I'm talking about here. And let's move over to this plot. You can see that the nominal current here at 2.25 amps is as much as 10 times lower than the inrush peak current. That can create real problems. It can trip your breaker, and it can really degrade the effectiveness of your LEDs. Other aspect of this is that we're sending an inherently analog signal to an inherently digital device. And what I mean by that is every LED is going to have an onboard microcontroller. Most LEDs are controlled using that square wave that I was talking about, or pulse width modulation. And so when you're just cutting the power to them, this is a problem for the LEDs, because for starters, they were never using that sine wave in the first place. All LEDs are direct current, not alternating current, and they have a very narrow operating range for their forward voltage and forward current, which means that the driver has to take that sine wave, rectify it, and transform it down to get the precise electrical characteristics necessary for the LED that it's operating. What that means is that every time you use analog dimming to get a lower light output, instead of getting a lower light output directly, like you might from an incandescent source, what you're doing is you're just screwing up the power supply to the LED, and the driver has to figure out what that signal is supposed to mean, clean up the power that you just screwed up, and then try to give you some kind of meaningful feedback. So that's the problem here, is that we're sending an analog control signal that is based on screwing up the power supply to a device that wants neither of those things. So let's talk about the outcomes then. There's a lot of outcomes here. So the obvious thing: reduced efficacy, reduced lifetime, reduced reliability. That's the big one. They just don't operate as well on analog dimming. And so a lot of the performance characteristics you get from LEDs won't be realized by an analog dimming system. Now, it gets worse though, because we've got a whole host of god awful behaviors that LEDs can engage in when they're being dimmed by poorly compatible drivers or poorly compatible dimmers. There we go. So flicker is oftentimes driven by the inrush current. And here we've got my dimmer here. So if I bring this up to max, it can be kind of hard to see, but it's flickering at a very high rate. And what drives that behavior is that inrush current incompatibility. So that's that spike that's happening every time at the start of the duty cycle. So you get this high frequency flicker that can be very debilitating for people. Now, another problem that's common with analog dimming, and so flicker is a forward phase dimming thing. But even if you move to a reverse phase dimmer, you can have dead travel on the dimmer. And dead travel is simply when you are moving the dimmer, but getting no change in the light output. So that's dead travel, meaning it does nothing even as you move the dimmer. That's frustrating. You also have pop on. So when you're at 0 and you bring it up to the lowest dimming and you get nothing, you keep on bringing it up, and then all of a sudden it jumps up to 50%. Oftentimes you can then at that point bring it back down and get a lower light output level. That's pop on. And then you have dropout. And that's when you're dimming it from a high setting and you bring it down and it just drops out halfway down the dimmer without letting you smoothly go to 0. Finally, you have ghosting, and that's when your light source is still active even when the dimmer is turned all the way to 0. And blinking, which means that it's not getting adequate power to stay illuminated. So it's trying to kick on, failing, turning off, kicking back on, failing again. And then you get a slower blink. The last thing you can get, and that's probably the most destructive outcome, is just this high-pitched squealing hum coming out of your LEDs. So there you have it. Compatibility in dimming is becoming less of an issue as essentially everything is transitioning to reverse phase. But in retrofit situations, it's still a real concern. And even with the right type of dimmer, you still have a variety of weird behaviors, because you might not get ghosting and blinking like that poor little bastard had. However, you still get pop on, drop out, and dead travel on a variety of analog dimming devices. Should talk about sensors, and sensors are a big part of what makes a lighting system truly intelligent and responsive. So we have just 3 basic types of sensors, so it's fairly straightforward. 2 types of motion sensor, as well as a photocell. Now, the big reason we utilize sensors is for automated control schemes of a variety of different types. The biggest ones are vacancy and occupancy control schemes, and that's what we're primarily using motion sensors for. And then for photocells, the main thing you want to use it for is daylight harvesting, or in the case of, say, an exterior security light like this one, you have a photocell right here at the center of that luminaire. And that photocell is basically just going to tell the luminaire, don't turn on when there's daylight. So passive infrared sensors are what they sound like. They are passive, and therefore they consume less power, and they're viable on a battery powered retrofit type device. For example, the one to the far right, which is the one the Hue system utilizes. So I can grab that one off the wall because this is the device I utilize at home. I actually really like having a sensor in my space in terms of making that system responsive. It's wonderful to open my front door and have my living room greet me by turning on all the lights. So I love the responsiveness of a motion sensor in a lighting system, but that doesn't come without concerns, problems, and drawbacks. So let's dig into some of those here in a minute, so that we can take a look at what we need to do to make these sensors really work well. So the first thing we need to consider is the field of view. So PIR sensors absolutely require a line of sight. And in fact, basically what PIR sensors do is they have these beams emitted from, or these beams of detection going back towards the sensor. And what's happening here is the sensor detects motion when you cross more than one beam. So what it's really seeing is large movements, gross movements. That's why you see the compartmentalization of these sensors. It's maybe a little hard to see. Yeah, it's not going to show that to you. But these sensors are largely compartmentalized on their surface, and that's to get different angles for these different beam sections. So they're very good at picking up large movements, which means that that they're great for things like hallways and stairs. In fact, in the engineering units, these are in our stairwells, and that's what turns the lights on for you when you're there late at night and no one else is. They're of course less sensitive as you increase your distance away from these devices, but you can solve that by adding additional sensors because they're not that expensive to add to your lighting system. We can also talk, instead of PIR, we can talk about ultrasonic sensors. Ultrasonic sensors are a very different technology. They don't require line of sight because what they do is they use a set of speakers to ping the room at ultrasonic frequencies. And so the way they detect motion is by detecting changes in the response from when they ping the room. So these are great because they can see around barriers. So for example, in a bathroom, they're the sensor of choice because they can see around the bathroom stalls and not turn the lights off on you when you're spending too much time surfing the web instead of finishing up and getting back to work. The other thing they're great for is capturing fine movement. Because you don't have to cross beams like you do with a PIR sensor, these things can capture very fine movement as they ping the room around them. So it's great for things like computer labs or workspaces where you expect your users to sit down and not move too much for a long period of time, because the typical size of movement you're looking for a PIR sensor is around 3 feet, whereas a ultrasonic sensor that is close enough to you can detect the movement of you just typing or writing at your desk. Now, of course, we have the ultimate solution is a dual tech sensor. So we can simply add both a PIR and an ultrasonic sensor to a device. And in fact, that's what this device is set up to do. You can see there's actually a window in the middle here that's not being utilized. And that's where the PIR sensor would go in this device. So a dual tech sensor gives you basically the best of both worlds, and it allows the sensor responses to cross-check against each other so that you have fewer false positives and false negatives, because that is the main drawback when we're utilizing these sensors. You don't want to set them too sensitive, because then the lights are turning on and off all the time for no reason. And you don't want to set them to too low of a sensitivity, because then they don't respond when occupants enter the space. So commissioning, again, is very important here, because if we want this to be convenient, and that's the big advantage of these sensors, then we need to get the sensors set up correctly to make that convenience a reality. So let's go back to our classroom from before and consider how we would place sensors in a classroom like this. So let's take a look at this in a little more detail then. First off, your PIR sensor, again, is for your gross movement. And so that's going to capture people entering the room at either of those two entrances on the north side of the room. Of course, this requires line of sight to capture those large movements. So you want to have those fairly centrally located so that the array can capture the edges of the room up on the north side. Now, with ultrasonic sensors, you again wanted this in the center of the room because you want to cover those desks in the middle, because that's where all your fine movements are happening, which will keep your system from turning off on people just sitting down and working. Some things to consider with these sensors: you do need about 12 feet of spacing between each of the ultrasonic sensors, and that's to eliminate crosstalk. Keep in mind, they're pinging the room, and if they're the same sensor, they'll be pinging the room the same frequency and listening the same way. And so if you have them right on top of each other, you can get crosstalk between your sensors, and that'll lead to an increase in both false positives and false negatives. One other consideration is HVAC units tend to create problems for both types of sensors. So if you imagine passive infrared is detecting the heat signature of a person moving around the space. So similarly, hot and cold air can interfere with that detection and lead to false detections or lead to decreased sensor sensitivity. So you don't want to place them right next to the vents in your HVAC system. So this is a reasonable placement. And the thing I would check in the documentation for the sensor, I'm not asking any of you to do this, but what I would do to check to make sure this works is I would check the range for the passive infrared. And what I would want to see is that the passive infrared sensor reached these doors, but didn't go way beyond them. Because you do want to cover those doors. You just want to make sure not to cover the hallway, because again, you don't want to turn on the lights when someone's just passing by. Let's talk about control schemes. So different ways that we're going to utilize our various control surfaces and sensors to create intuitive and convenient systems for our occupants to utilize as they interact with the space. So some basic manual control schemes. First off is just local control. Give the users in the space the ability to manipulate their own lighting. And you wouldn't believe how common this is overlooked in office settings. You don't have any local control for individual office workers because you just have general overhead ambient lighting. So a way to increase the versatility of that system and increase user acceptance is to simply add task lighting in each of your cubicles so that the employees have some form of local control over their lighting. Another important aspect is zones. And so zones is basically what we set up by giving a set of 3 lines of light that are similarly controlled by 3 different switches. This gives you 3 different control zones that can be dimmed and switched separately, meaning you can place light where you need it and leave the lights off where you don't need it or don't want it. And finally, the last really common manual control scheme is timers. And so we can use timer switches in things like utility spaces. Your laundry room in your apartment complex probably has one of these. And that's simply so that you can have light as long as you're in that space, but then they expect you to just walk away and not care about that space. It's not your space, it's a shared space. So, what do you need to turn the lights off for? A timer switch will ensure that those lights do turn off again, even if you don't have a sensor to do it for you. And of course, these are cheaper and easier to install. They're literally idiot proof. You do not need an electrician to install a timer switch. Literally anyone can do it. Whereas adding a sensor requires understanding how to get that sensor to control the luminaires in your space. Moving on to scenes. Scene controllers are wonderfully diverse. They are extremely versatile because you can quickly serve very distinct visual tasks or very distinct space uses. Here's a great example of a kitchen where you have a nice bright morning scene so you can quickly prepare your breakfast and start your day. You have a daylight scene here, which makes use of the clerestory windows above the cabinets that are just outside of this picture. You have an evening scene so that you can see what you're doing late at night. So when you want to get that midnight spoonful of peanut butter with chocolate chips in it, not that that's something I do, totally is. So when you're getting that midnight snack, you can just use the minimum level of lighting to interact with the kitchen without it waking you up. And then, of course, if we're going to use a scene controller, we might as well create some beauty in our space. And a scene controller can be quickly and easily set up to create a wide range of very specific things. So again, scene controllers can be versatile and convenient. They aren't necessarily intuitive unless you have a clear plan, a clear design approach, and clear labeling to go with all of that. Now, where scene controllers are particularly useful is where you're trying to consolidate and coordinate multiple zones. So let's say you have a whole bank of switches and dimmers that control the chalkboard lights and the overhead lights in a lecture hall. And then you've got lights by the entryway and a spotlight on the podium. Well, it's far easier to just have a scene that says projector. And then you can cut the lights in the front, put more lights in the back, highlight the presenter, and make sure that projection screen is clearly visible. Scheduling. Scheduling is a control scheme that lacks a lot of nuance that I might want from a proper control system, but nonetheless, it's still in widespread use because anytime you have a building automation system, you can definitely get scheduling, even if you can't get one of the other more nuanced control schemes that utilizes sensors. What you need for scheduling is extremely well-defined use cases. So, for example, an after-hours shut-off in a retail space makes sense for scheduling. Dimming during periods of reduced occupancy. In this case, this is from the Philips Hue app. So this is showing a wake-up routine. So I do actually utilize this at home. I love having the lights scheduled to come up to full brightness. And so it actually starts that routine just before my alarm goes off, and about 5 minutes after my alarm goes off, it's up to full brightness and a crisp daylight white, which really does help lift me up out of bed and get me rolling straight away at the start of the day. So that, I think, is one of the great uses of scheduling. Security routines is another aspect. Parking lots and parking garages might use scheduling to reduce their energy consumption. This can lead to significant energy savings, especially because these systems are generally pretty inexpensive And oftentimes you already have the capability in your architectural system without actually adding a dedicated lighting control system. So scheduling is in fairly widespread use for those reasons. Now, the more nuanced solution to all of this is, of course, occupancy and vacancy routines. So these are, again, very convenient systems because you can have your building respond to the occupants as they come in, and it doesn't have to worry about the time of day. So you can have these systems respond the same, whether it's 1 a.m. or 8 a.m. So that's a big advantage because it's responding to an actual detection of a person in the space. It's relatively easy to integrate these sensors. You'd be surprised how easy it is to integrate these, even in a retrofit setting where you don't want to run wires, you don't want to punch holes in your walls. You just need to add a control box to the back of your luminaire that responds to a signal from a battery powered sensor that you can literally just sticky to your wall. So they're very easily integrated. That said, like we discussed earlier, they do require commissioning because you don't want them to be too responsive. You don't want them to ignore when users enter the space in exactly the way you expect them to. They do lead to outstanding energy savings, and the difference between occupancy and vacancy largely comes in the energy savings. So an occupancy routine means that the sensor will turn the lighting system on when it detects someone entering the space. And then when it stops detecting movement, it'll wait a certain amount of time. That's called your dead band. It'll wait a certain amount of time before turning the lights off. The vacancy routine is basically just the second half of that, where it won't turn the lights on when someone enters the space, but it will turn the lights off when it stops detecting movement. Now, the simplest solution to not turning the lights off on people sitting in your spaces is to set a long dead band so that there's more opportunity for the person in the space to move around enough for the sensor to detect before the sensor decides it's time to turn the lights off. So these are particularly useful in places like transition spaces, so hallways and stairways. They're great for security lighting on the exterior of a building. And they're also great for all types of interiors, especially with an occupancy routine. Vacancy, like I said, has better energy savings. And you can dramatically increase the reliability and the amount of false positives and negatives by using a networked sensor array. So that's becoming more and more viable as we have more and more often loaded these types of sensors into luminaires themselves. An LED luminaire already has a microcontroller on board because that it needs it for the driver. So there's no reason for it not to also utilize a sensor and respond to the sensor's inputs. And if you have a whole series of these luminaires inside your space, there's no reason you can't network the whole set of luminaires and get a ton of information to make decisions on. Daylight harvesting. Now, this is the next step down the path of complex control schemes. So the main thing you're doing with daylight harvesting is you're making better use of your side lighting, so your windows and your top lighting, or skylights usually, by turning off the lights when you have plenty of light already in your space. So that's the harvesting part of daylight harvesting, is you're basically saving energy by utilizing the daylight to light your space instead of utilizing your interior lights and having your lights respond intuitively to those light levels by using a photo sensor to shut them down when they're clearly not needed. Again, these are the type of sensors that do require commissioning, meaning verification in the field that they're functioning and behaving the way you might expect them to, because you definitely don't want them turning the lights off on people when they just get a little bit of sparkle in the photo sensor. And you're also going to need different zones of lights. So either zones or individually controllable lights to make use of this, because most likely, and this is a great example right here, what you're going to do is you're going to turn off the zone of lights closest to the windows and leave the lights back deeper inside the middle of the space. You're going to leave those lights on so that the light level doesn't drop too much as you get away from those windows. Now, obviously, there's huge energy savings to be had here. But I think the other important aspect of this is actually the health and wellness and user acceptability part of this control scheme. And that's because you can integrate roller blinds with your daylight harvesting system. So you can actually use it not just to turn lights off because you have plenty of daylight. You can also use it to automate your glare control. So if you have a high level of daylight on your work surfaces, you can use the photosensors to detect that and pull down these roller blinds to cut that glare. And as the light level decreases from daylight, you can bring the roller blinds back up to compensate. So there's a lot to be had there in terms of health and wellness and user acceptability in the space. And the last control scheme I want to talk about here is color tuning. This is not something you're going to need for this class. I like to talk about it because I think this is the most interesting, most nuanced, and most versatile approach that we can utilize these advanced control systems for. And it also directly utilizes my research. Now, there's three really common forms of color tuning. The first one is simply tunable white, which is what I'm showing here. So the idea of tunable white is that the natural daylight cycle, as you move through the day, you start with the sun low in the horizon and very warm. It's the reason why a sunset is orange, right? Because you have more atmospheric attenuation and specifically me scattering, not Rayleigh scattering. Rayleigh scattering is what makes the sky blue. Me scattering is what makes sunsets orange. I'm not going to explain it. Wikipedia will tell you everything you need to know. So what you have is a orangey glow or a low CCT at the start and end of the day. And when the sun is high in the sky, you have a very high CCT. And this is our natural daylight cycle. And your circadian system responds to that as well. So that's why you use a blue light filter late at night to help you fall asleep, and why you use a high brightness, cool white light in the morning to wake you up and get you started on the day. And so these circadian photobiology cycles can be mimicked by a simple dual color white light source so that you can shift from warm white in the evening usually to cool white throughout the day. Another really common color tuning scheme when you have a dual white tunable white system is dim to warm. I think those are kind of silly, but there's a lot of nostalgia and familiarity surrounding those dim to warm systems because that's what incandescents used to do when you dim them. So we can mimic that same cycle in LEDs now. And so Edison bulbs are a prime example of that, where you actually do have dual white LED systems inside those so that you can dim them and get those super low CCTs when you want them. And then finally, the last aspect of this would be manipulating your color rendering. So if you have a multi-channel system, these are going to require more than just dual white, but you can tailor your gamut for specific visual experiences. So you can have highly engineered gamuts that create highly specific light to enrich the visual environment. This is our last piece of the day because I wanted to tie this all back in to your projects, specifically the control requirements included in ASHRAE 90.1. And when you look at the table like this one right here in the ASHRAE standard, you're going to see basically this series of required controls. And if you go and read the sections, it's going to give you a little more detail. but I do want to take a moment to talk about each of these. So first up, we have local control, and that simply means some sort of controls for the occupants to use in the space near the light sources. So the basic idea here is a control for end users, not a centralized control system, within line of sight to your luminaires. Restricted to manual on simply means you can't use an occupancy routine. Vacancy is still fine, but restricted to manual on means that you would only allow the system to be turned on by those manual local controls. Restricted to partial automatic on is a similar idea. However, in this case, you can use your motion sensors to do a occupancy routine that doesn't bring it up to full brightness, but rather allows a minimum level of light in the space so you can see what you're doing. And then that gives you the ability to walk over to the wall, find the switches, and bring the system to full on if that's what you need. But what this does is it encourages energy savings by requiring your users to actually make the decision to turn the lights all the way on or on at all in the case of restricted to manual on, instead of just always blasting those lights every single time it detects movement. So this enhances the energy savings associated with occupancy and vacancy routines. Bi-level control can be realized in a huge variety of ways. A dimmer is more than bi-level control. So if you've put a dimmer in the space, you're good to go already. Scene controllers usually will get you there. Also just zoning your lights. So in that example classroom that we were utilizing earlier, we had 3 zones of lights, and that's going to get you multiple light levels in your space. So there's a variety of ways you can get to bi-level control. Daylight harvesting. These are a little more complex, and I'm not asking you to add anything into your lighting plans to actually realize these requirements. You can just add them to the table and say, yes, we need daylight harvesting. If you really want to understand how that works, we have a dedicated controls class where we'll dig into that. For the rest of you, just put it in your table. But the basic idea here is what you need is a photocell, and specifically a photocell that sees the part of the room, in this case, nearest to your windows or your side lighting. And in this case, the top lighting case, you want those photocells to clearly see the work plane below skylights so that it can detect when light levels are high enough to turn off the lights in those zones. Automatic partial off and automatic full off can both be realized in a variety of ways. Sensors are the obvious solution here, but you can also do that with your timer switches, for example. So it's basically any part of the system that will allow the lights to automatically turn off once the space is no longer occupied. And there's a variety of different approaches you can use for that. For example, a scheduled shut off is also a way to automate turning off your lighting system. It's generally not as effective as something that's automated using sensors. So this is in its own category where you would have the control system itself have a scheduled time of day shut off when you know that no one should be in that space anymore. So those are the basic control schemes and a basic idea of how you would utilize the control devices and the control schemes that we discussed today to get you there. This does bring me to the conclusion of my controls lecture. I appreciate your time. This is one of the most worthwhile topics in lighting, if not super interesting. It's super powerful and really helps us realize the full potential of our lighting systems. So controls is not something you want to overlook. And also commissioning those controls and verifying they actually work as expected is not something you want to overlook if you really want to get the full capabilities of a proper control system. And I look forward to exploring this with you all in person tomorrow and remotely on Thursday. Have a good night.